This is section 16.6, integrals for mass calculations. Basically, we're going to spend one section to just do a bunch of random applications of double or maybe triple integrals, depending on what examples are in here, that are not just geometry applications. So what we've done mostly with double and triple integrals is we found areas, volumes, and then we did a little tiny thing where we did the average value of a function. Finding the center of mass of objects is another application of integrals. There's lots of applications of integrals, but this is the last one we'll do before we jump into the crazy part of the class where we do chapter 17, which is all about vector fields and vector calculus. The objects that we'll be dealing with in this section are mostly functions where the input is a point in the plane and the output is a number. So let's jump in and see what's going on. Basically, we're going to start out by reviewing some physics terms. If something is resistant to change in motion, that's its inertia. Things with mass seem to have inertia. And we try to measure stuff like this using mass and force. So let's see. The creator of this table apparently has a problem with the fact that the US doesn't use the metric system. Don't worry, NASA uses the metric system. So yeah. Anyway, in the metric system, mass is in kilograms, and then force is mass times acceleration. So force must be kilograms meters per second squared, and these are called newtons. In the imperial or US customary system, how do we even measure mass? I mean, force is in pounds. I think they're called slugs, maybe? No one cares. It doesn't matter. Sometimes we'll have force and we'll measure it in pounds. If we're measuring mass, we're basically always in a scientific enough situation where we'll just be using the metric system. Okay, how does the center of mass work? So the way center of mass works is you try to pick a point where the moment of the system about this point is 0, which means that it will balance about this point. So let's see. These two objects are 6 centimeters apart. One of them is 4 kilograms and one of them is 2 kilograms. If I try to balance this shape right in the middle, it will tip toward the 4 kilogram side because the 4 kilogram side is heavier. To try to fix that, I'll need to come over here somewhere so that the 4 kilogram side has less. I'm trying to avoid using more physics terms than I have to. So that the 4 kilogram side has less moment. I'm going to have to talk about that a lot, about the point that we're balancing. And the 2 kilogram side can get more action in this direction. So let's try to figure out where that center of mass is. Let's just say declare some place to be x equals 0, then the total moment. Moment is mass times displacement. So the total moment is, well, this 2 kilogram object, since I've declared x equals 0 here, is 2 kilograms times 0 meters plus 4 kilograms times 6 centimeters. So the total moment is 24 kilogram centimeters. The center of mass you get by taking the total moment and dividing by the total mass. The total mass here is 6 kilograms. So the center of mass, the average location, this is average location of the object, is 24 kilogram centimeters divided by 6 kilograms. And I get 4 centimeters. Since I declared x equals 0 to be here, I end up right here, 4 centimeters from the left side. This choice of x equals 0, it was kind of arbitrary. We could have chosen a different point to be x equals 0. If you choose a different point to be x equals 0, you still get the same final answer. Your answer just will be a different value of x, but it'll still point you at the same place. So for example, if I declare, let's just do the same whole thing in a different color. If I declare this to be x equals 0, then the total moment this is an S, the sum of the moments, would be 2 kilograms times minus 6 centimeters, plus 4 kilograms times 0. So the total moment would have been minus 12 kilogram centimeters. And then when I divide by the total mass, minus 12 kilogram centimeters divided by 6 kilograms, I would get minus 2 centimeters, which would tell me to go to the left by 2 centimeters. So I would be over here. So this kind of thing where you can't really solve the puzzle unless you pick a coordinate system, but the coordinate system is totally up to you. This is pretty standard in like physics situations. So let's just try to summarize what's going on here. The moment about a point is mass times displacement. To completely balance a system, you'll need the sum of the moments to equal 0. If you have x bar, the center of mass, the moment about the center of mass for a point xi, I don't know what's going on with this question. I don't know what's going on here. But we're trying to find the place where the sum of the moments equals 0. So if we just pick, like if we instead had chosen this point as x equals 0, then the sum of the moments would be, well, this would be 2 centimeters times 4 kilograms. And this would be minus 4 centimeters times 2 kilograms. So in total, I get 0 for the sum of the moments when I have actually chosen the like balancing point. Sorry, I'm not sure what we're going for here with these questions. So how do we find the center of mass for a one-dimensional system in general? Well, you should imagine if you had n objects, what would you do? Well, you'd start by adding up all the moments of all n objects, and then you'd add up all the masses of all of the n objects. And whenever you see someone doing this, where they're adding up like an indeterminate number of things, you should, because you've had 3 semesters of calculus, you should think, well, why would there only have to be n? Why can't we have infinitely many? And then this sum would turn into an integral. But anyway, the center of mass is the sum of the moments over the sum of the masses. And it looks like we've got, we're calling that m0 over m, which, whatever. I already did this problem. I don't know what we were supposed to do on the first page. Let's do the second one. So now I have a whole bunch of masses. The coordinate system is given to me, which is kind of a disappointment because part of the whole point of this is that you can pick the coordinate system and you still get the same answer no matter where you put the coordinate system. So, also the quotes, I don't know if you've been looking at the quotes every week or how I'm running the class with regards to the quotes, but like the fact that there's a symmetry here where things can move around where like you move the coordinate system around and the physics works the same is called a symmetry. And as a result, that means there's a corresponding conservation law, which is this like really important fact. And I think it's the quote and like extra stuff next week. But depending on how you're viewing this video, that might not even mean anything. So whatever, let's just move on and find the center of mass. To find the center of mass with this coordinate system, we find the sum of the moments, which is, I guess I have 5 kilograms at minus 3. 5, so it's like mass times displacement. So 5 times minus 3 plus 4 times 0 plus 2 times 2 plus 6 times 4. So the sum of all the moments is 13. And then the sum of all the masses is 5 plus 4, that's 9, 15, 17. Combine all these together, and you get that the center of mass is at sum of the moments over sum of the masses. So this would balance at x is 13/17, which is around here. Okay. If instead you didn't have discrete objects, but say you had like a long rod, but the rod gets like denser or thicker at one end. I don't know. It doesn't have to get physically larger, but it could be denser over at one end. you could instead say, well, sure, I want to use the same formula, but instead of having finitely many objects, I have infinitely many objects. How can I possibly do that? And the answer is you just cut it up into infinitely many, infinitely small objects. That's how calculus works. Say this is a little tiny bit of the distance, and then you can find a little tiny bit of moment and a little tiny bit of mass and add them all up. So a tiny bit of moment and a tiny bit of mass, add them all up and divide, and you'll get the center of mass. So this will be our calculus formula for how to find the center of mass. Say that you have something that has, like the rod has variable density. So the density at one point is different than the density at another point. Well, in that situation, what would the moments be? So a little bit of moment would be, let's just say this is x equals 0. Well, you'll have a slice that's at a certain location x. You'll have an amount of it that's dx, but its mass will be the density times the amount that there is. So the moment of this little tiny piece will be its mass times its displacement. So it's density times dx times x. So this is the little bit of moment. And then the mass is just add up all these little bits of mass. So this will be our formula. The center of mass is located at add up all the little bits of moment from A to B over add up all the, this doesn't fit here. Let's just name them. We'll just call it the total moment over the total mass. The moment is add up all the little bits of moment. And the mass is add up all the little bits of mass. Hopefully there's an example up next. Nope. Okay, I guess that was in Calculus 2. Unfortunately, a lot of people skip these sections in Calculus 2 and Calculus 3, so it's possible that you missed this. But whatever, the point is that, I mean, kind of like the summary of Calc 2 is that you can find anything by adding up all the little bits of the thing. So you have like all those formulas. And this is just more of that. So say we want to find the center of mass of a 2D region instead. Again, we're going to say that it has a density function, right? Oh dear. Okay, let's assume that it has a density function. Which is this kind of object over my head where you input a point, xy, like this point, and at that point, the object has a certain density. Well, if we want to figure out the center of mass of this region, I need to figure out like the x-coordinate and the y-coordinate of the center of mass. So I'll say like, here's my target point maybe. Well, I don't know, maybe it's like down here. X bar, y bar. To figure out the x bar, the x coordinate of the center of mass, I need to figure out how much mass there is away from the y-axis. So x bar is going to be the moment about the y-axis divided by the total mass. And y bar will be the moment about the x-axis divided by the mass. So how do we like deal with this? Well, to take a 2D region, you can cut it up into little tiny slices. And a little tiny slice, in Calc 2, we were stuck cutting up either one way or the other way. In Calc 3, we say, whatever, I'll cut it into this little tiny slice that's dx by dy. Or if the shape needed to be done in polar coordinates, we could do r d theta. And you can imagine how this might continue into 3 dimensions. But we're not going to try to do super crazy problems. We'll just try to like get the idea and do a couple of questions. So the mass of a representative piece, well, the mass of this little thing, I'll call it dm. Well, the mass is related to the area, so I'll multiply by the area. And what I need to multiply by is the density function, because like the area will be in square meters. and the density of a 2D object is in like kilograms per square meter. So this is the mass of a representative piece. So the mass of the entire thing is add up all the little bits of mass, which is add up the density function times dA. This dA might be dx dy, or it might be dy dx. It's probably one of those. It could also be rd theta in polar coordinates. Okay, now let's look at the moments about the x and y axes. If you want to know what is the, let's find the moment about the y-axis of this little shape. Well, its distance from the y-axis is x. So we're finding the moment about the y-axis. It's going to be mass times displacement. Its displacement, though, is x. Its mass is density times area. So it's rho x dx. Oops, rho x dA. That means that I can find the moment about the y-axis by just integrating this, and it's a double integral because I have dA. Similarly, if you're trying to find the moment about the x-axis, well, the mass stays the same, but the distance changes. Now the distance is y. So when I find mx, it's going to be the same deal, except now the displacement, the amount I am away from the axis, is measured as y. So the center of mass is like no big deal. It's got 3 double integrals. The only thing that can make it challenging is if this density function is crazy. So let's just write down these formulas in this box so we can have it done. The moment with respect to the x-axis is I'll need to add up. I need displacement from the y-axis. Displacement from the x-axis is called y. And then I need to multiply by the density dA. This measures the net impact of the mass in the y direction. This is like the amount that the object wants to tip away from the x-axis. Now the moment about the y-axis, well, it's going to have the mass. Here's the mass times the displacement, and the displacement from the y-axis is called x. This is how much the object wants to tip away from the y-axis. And then I think we get to put the center of mass formula. Okay, the center of mass is the point where lamina is supposed to be, it's like a flat object. So density will be measured in like kilograms per square meter. I don't want to think about it as a solid object. I'll think of it as being really, really thin, like a piece of paper. You would measure the piece of paper's density in like kilograms per square foot or per square meter, not kilograms per cubic foot of paper. That would be weird. So that's what this word does for us. Think of 2D objects. So it's the point where the lamina can be balanced. The center of mass is the point where all the mass can rest. Yep, we got it. Okay, this is a nice way to think about it, that y bar is the y value, where if you put all the mass at that y value, y bar, you'd get the same amount of like tipping away from the x-axis. So you'd get the same amount of torque around the x-axis. Similarly, if you put all the mass at x bar, then it would tip the same amount away from the y-axis. So the center of mass is the point where if you took the entire object and you pretended like the entire object was all focused at that center of mass, it would act the same physically. There's some cool videos of where you can kind of like watch a gymnast or an acrobat like doing stuff in the air, but you'll watch that they're stuck to their center of mass. Their mass all kind of acts like it's at their center of mass. So when they jump, their center of mass just follows the same path that like any object follows. But they'll be like twisting around their center of mass, and it's kind of strange to be like stuck to your center of mass. Anyway, the coordinates of the center of mass are x bar is the moment about the y-axis divided by the mass, and y bar is the moment about the x-axis divided by the mass, where we use integrals to find all these things. So we got these in the other box, but I'll just write them again. Moment about the x-axis, the displacement is y. Moment about the y-axis, the displacement is x. and the mass doesn't have the displacement term in it. If your density function is 1, so if you are, instead of thinking about a physical object, if you're instead thinking about a geometric object, like a triangle, as opposed to a triangular piece of steel, in that case where the density is 1, then we don't call it the center of mass anymore because it's a geometry object instead of a physical object. If you're looking at a geometric object, you would call the center its centroid, where for a physical object, its center is called the center of mass. We just said that like 13 times. I'm skipping that. Hopefully we get to do some examples. Okay, great. So here's a specific lamina, a 2D shape. We're looking in the xy plane. Y equals 4 over x, looks like this. Y equals 0 is the x-axis, and x equals 1 is here. Whenever I get a picture like this, I like to label the intersection points as soon as I get them. So if I plug in x equals 1 into my function, I get y equals 4. So we're trying to work with this planar lamina between y equals 4 over x, y equals 0, x equals 1, and x equals 4. When I plug in x equals 4 into my function, I get 4, 1. So we're looking at this region. Now, it tells us that the density is actually different at each point of this object. It gets denser and denser as we go further to the right. So I've got something like this, shape like this, but it's really, really light over here, and it's really, really heavy over here. So this says find the mass and the center of mass. I guess I'll find the mass first because I have to do that anyway on the way. The mass is add up all the little bits of mass. I've got everything in terms of x and y, so using dA as dy dx seems fine. The density function is x squared. dA will be dy dx. Whatever I have as the outermost variable, I just give it numbers. So the outermost variable, the x's go from 1 to 4. And then the inner integral, those bounds, can depend on x, and that will be our bottom function and our top function. The bottom function is y equals 0, and the top function is y equals 4 over x. This integral will give us the mass of this object. So first I'll do the inner integral. The outer integral is just going to sit there. X squared is a constant, so its integral with respect to y is x squared y. The bounds are from 0 to 4 over x. When I plug those in for y, I get, this other integral is sitting here waiting for us. I plug in 4 over x, so it cancels one of the x's, and I'll get the integral of 4x dx. Well, integral of 4x dx is 2x squared from 1 to 4. So I plug in 4 and plug in 1, and the final answer here is that the mass is 30. And this is a little weird that there's no units on here for us to use to check things, but I guess the mass is 30. Notice that this isn't area. Like, we used a density function. Oh well, mass is 30. Okay, we're headed for the center of mass. To get the center of mass, you just do 2 more integrals. So you want the moment about the x-axis. The moment about the x-axis has the mass in it, but it also has displacement, which is when you're trying to figure out how far away you are from the x-axis, that's called y. Like how far up did you go? Well, I went y up. So the integral is just the exact same thing, except the integrand is different. Notice that if you've been like really internalizing what's going on in chapter 16, the bounds are just telling you the region that we're talking about. So the bounds describe the region, and then the function we're integrating describes like whatever's going on in the region. This is different from how you thought about what was going on in like Calc 1 and Calc 2. But in Calc 3, we finally get almost all the geometric information about where things are happening up into the bounds. Since these are all happening in the same place on this like lamina, then the bounds are all the same, and we just change the integrand. So we get different integrals here, but it's no big deal. The outer integral sits here and waits for us to be done. The integral of x squared y, x squared is a constant, so I get x squared times half y squared from 0 to 4 over x. Plug in 4 over x, and now it cancels all the x's. And I get just 8 dx. This is 24. So the moment about the x-axis is 24. The moment about the y-axis, same setup, same region. But now, instead of the mass times the displacement away from the x-axis, now I'm asking how far away are you from the y-axis, and that's called x. So my integral is now, instead of x squared y, it's x squared x. Here's x squared x. Okay, this integral is x cubed y. I plug in 4 over x, so I'm going to have 4x squared dx. This comes out to 4/3 x cubed from 1 to 4. So I have 4/3 of 64 minus 1. It's 4/3 times 63. So I get 84. Okay, now these are not the final answers. One of the final answers was that the mass is 30, so that's good. But the center of mass is a point. It's not just the moments. The moments are there to get us to help find the point. So the point has an x-coordinate, which is how far away we should be from the y-axis. What was my? My was 84. So 84 over 30. Does this simplify in any reasonable way? This is like 7 times 12. And this has a 6 in it also, so we'll be able to divide both by 6. That's not right. Divide this by 6, we get 1, 4. Okay. 14/5 is 2.8. And then y bar is, well, use the moment of how far away you should be from the x-axis. That was 24. 24 over 30 is 0.8. So the center of mass is at 2.8. 1, 2, 3. 2.8, 0.8, which is like right here. It's good that the center of mass ended up inside the object. That doesn't always happen, actually. There are objects where no matter how you hold them, you cannot balance them on a point. The easiest example I can think of is a compact disc. I don't know if you even all have interacted with CDs, but a compact disc, a CD has a hole in the middle, and the center of mass is in that hole. So no matter where you try to there's no point on a compact disc where you can balance it. It'll always tip over because it's missing the part where the center of mass would be. Yeah. Okay. Anyway, center of mass, just not scary. Like you do a bunch of double integrals, but once you've found the bounds once, they're done because you're dealing with the same region over and over. So you find the bounds and use those bounds over and over, and then you just do 3 different integrals. And as long as you can keep track of what in the world you're doing, you'll be fine. Okay, let's do 3 dimensions while we're here. The point of this is that all this stuff works just as well in 2 dimensions as it does in any number of dimensions. So we'll switch our perspective here to where now our density function takes an input of a point in space, and the output is a number. Okay, how do you find, so let's just do this. We're going to take our blob object, whatever it is, and I'll slice it up into little tiny pieces. And the little tiny pieces will have volume dv. Well, to get mass, a little bit of mass would be the density times the volume. So the mass would be the integral of all the little bits of mass. Because this is dv, I'm going to be working in 3 variables. This is a triple integral. Nice. Okay. There will be a whole bunch of different moments. How do you get away from the yz plane? To get away from the yz plane, you just make x something other than 0, because this is x equals 0. So how far away are you from the yz plane? That's called x. So the moment is you multiply x times the mass. To get away from the xz plane, well, the amount that you are away from the xz plane is called y. And the amount you are away from the xy plane, here's the mass, and moment is mass times displacement. The amount you are away from the xy plane is z. So, yeah, how do you get the center of mass? Well, the center of mass will have 3 coordinates, x bar, y bar, z bar. And you get them by just dividing the moments by the mass. So this one, I want to know how far away I am from the yz plane. This one, I want to be away from the xz plane. And for z, I want to be away from the xy plane. We could keep going, like we could do 4 dimensions and 5 dimensions and 6 dimensions. And if you're, like, I keep saying this, but I'm worried that you don't believe me this ever happens. Say that your company is like Netflix and you gather a whole bunch of information about viewing habits and you want to find like what is the average person in this group? Like where is the center of this blob? Well, your dimensions might be like the amount that they like horror movies, the amount that they like action movies, the amount that they sign on every day, the amount, like, you might have tons and tons of dimensions, and these calculations will just still work. So we're doing them as though it's straight up physics all the time, but it doesn't have to be physics all the time. And even if it is physics, you can still at least do 4 dimensions. Like, that's pretty widely accepted. Anyway, let's do one object where we do a 3-dimensional object. We won't make it too crazy. This is just going to be a solid box. So we're going to do the coordinate planes. X equals 1, y equals 2, and z equals 1. So we'll have this solid box. This is our region. A little bit of that region, if we slice it up, would be a little tiny cube with mass density times volume. So the mass is going to be integrate the little bits of mass. And this density function, you should look at it and go, ooh, this looks kind of spherical. But then you should remember that the way you decide what coordinates you should use is almost always just based on the shape, like the region that you're integrating over. So even though this kind of looks like a spherical type density function, look at the region. The region's a box. It's a literal rectangular box, so we're going to use rectangular coordinates. So to get the mass, we'll just get x squared plus y squared plus z squared in here. It's a box, so the order doesn't matter at all, but dz, dy, dx works pretty well for us. The innermost integral is dz, so the bounds are from 0 to 1. The next one is dy, so we'll go 0 to 2. And the next one is dx, so we'll go 0 to 1. So this is our mass. We can do this integral. This is no big deal. So the z integral is going to be x squared z plus y squared z plus a third z squared cubed from 0 to 1. And all the other integrals are just weighting. When I plug in 1 here, I get x squared plus y squared plus a third. Then I can do the y integral. I'll wait to do the x integral until later. The y integral gives me x squared y, a third y cubed, and a third y. Go from 0 to 2. Plug in 2 for y. I get 2x squared plus 8 thirds plus 2 thirds. I could combine 2 thirds and 8 thirds, but whatever, I don't care. Do this integral. Get 2 thirds x cubed plus 8 thirds x plus 2 thirds x. This is all going to go from 0 to 1. So I plug in x equals 1 and get 2 thirds, 8 thirds, and 2 thirds. So this is 12 thirds. That's 4. So the mass of this box is 4. Let's keep track of all the answers we get up here. The mass is 4. And then I'll just make a place for our answer. We have 3 more triple integrals to do. I don't see any way out of this. Like, you basically are going to have to, we'll have to take this density function, multiply it by x, multiply it by y, multiply it by z, and integrate. And I guess I do see one way out of it, which is that x and z are completely symmetrical. So the one where we put x in the integral and the one where we put z in the integral will be exactly the same answer. Like x goes from 0 to 1, y goes from 0 to 1. X is squared, z is squared. The x's and z's appear exactly the same everywhere, so I know that the one with the z and the one with, oh, here's the one with the z, and the one with the x will be the same. So we are able to get out of a little bit of it. But let's do the other ones. So I'll do mxy. Same bounds because it's the same region. This was dz, dy, dx. But now mxy needs to multiply the mass by the displacement away from the xy plane. So we multiply it all through by z before we do the integral. Then just do it all. So take the z integral of this. I get half x squared z squared plus half y squared z squared plus a fourth z to the fourth from 0 to 1. Plug it all in. I don't know if you're, like, if you're able to get bored during this problem, I guess I just think of that as like a testament to how powerful this is. Like, the idea of triple integrals, taking a kind of complicated 3-dimensional problem and just breaking it down into such like easy to digest pieces that this problem is boring. Like, I'm a little bit bored by this problem. That's extremely powerful. I guess that's a pretty bad superpower, to be able to take something crazy difficult and make it boring instead. Anyway, let's do the y integral. The integral of y squared is a third y cubed. Y goes from 0 to 2. Plug in the 2. Oops, 2 times a half cancels. 8 sixths is 4 thirds, and 2 fourths is a half. Finally, the x integral. From 0 to 1, I get a third plus 4 thirds plus a half. Notice that I got punished for simplifying the sixths, because now I have to put it back into sixths after all. So this is 2 sixths, 8 sixths, and 3 sixths. 2, 8, and 3 is 13 sixths. That's mxy. myz will be the same thing due to symmetry, because the x and the z appear the same everywhere. Let's do one more. We'll find mxz. This is the moment about the xz plane. So it asks how far away you are from the xz plane. the distance to the xz plane is called y. So I'll have my density function, but then I multiply it by y. So I'll have x squared y cubed, and y z squared. Do the z integral first. Z goes from 0 to 1. Plug it in. Did the z integral. Now let's do the y integral. Y goes from 0 to 2. The x integral is still waiting for us. So I have 2x squared, 16 fourths, and 4 sixths. Will I learn my lesson? I think I'll learn my lesson and not reduce the fraction. Let's see if I get rewarded later. No, I won't. Too bad. Do the integral. I get 2/3 x cubed, 4x, and I'll reduce it now that I see that there's no more sixths from 0 to 1. So I get 2/3 plus 4 plus 2/3. This is 12/3 and 4 more thirds, which is 16/3. So this is 16/3. So what's my final answer? I have these 3 moments and the mass. The x bar is the one that was telling me how far away I was from the yz plane. Like this was the one that had x in it, divided by the mass. So I'll have 13/6 over 4. Z bar will be the same thing. And y bar is the one that had the y. The moment that had the y, all divided by the mass. I'm a little afraid to do this, but let's check to make sure that this point is actually inside the box. Okay, 13/24 means we don't quite go all the way out to 1 in the x direction. That's good. 4/3 is more than 1 in the y direction, but that's okay, because the y goes out to 2. And 13/24, yeah, okay. So it's inside the box. That's our reasonable way to check this answer. So what's the point of this? I mean, is like center of mass going to come back later in this class? No, absolutely not, like except on a quiz or exam or something. But the point of this is really the like feeling that if you know how to do something for a finite number of pieces, that you can just turn it into an integral. That was supposed to be the power of Calc 2. And then this was supposed to be like, hey, and by the way, if the little pieces have like dA or dV in them, then you would have double or triple integrals when you finished that process. So it's kind of awesome. You should do some practice ones. Try to like focus on getting the region to be working out correctly with the order, and just do some problems and try to get to the point where they're like a little bit boring. Look at this though. This is crazy. Oh well. Okay, that's 16.6.